In this video, we'll take a look at Newton's second law, what it states, how it applies to moving objects, how we use it to predict motion, and how to calculate forces. When a net force is applied to an object, it will accelerate in the direction of that net force. That's what Newton's second law states. Kind of straightforward. When you push on an object, it'll either speed up, slow down, or turn in the direction that you push it. Acceleration is rate of change in velocity. Velocity is speed and direction. So again, when a net force is applied to an object, it is either going to speed up. That happens when the net force is in the same direction as the object's motion. Here I have some free body diagrams. The arrows that are inside the box represent the direction that the object is moving. The arrows outside the box represent the direction of the net force. So in every one of these, the net force is in the same direction as the object's motion. And so every one of these scenarios, the object would speed up. This one would continue moving to the right and speed up. This one would continue moving upwards and speed up. This one would continue moving to the left and speed up. So again, when the net force is applied to an object, that object will accelerate. That object will either speed up, slow down. Slow down happens when the net force is in the opposite direction of motion. So again, all my free body diagrams here, the arrows inside the box indicate the direction the object is moving, and the black arrows outside the box represent the net force. And in all three of these scenarios, the direction of motion and the net force are opposite. So in all three of these scenarios, the object will slow down. This one will continue moving off to the right, but slow down as it does so. This one will continue moving up, but slow down as it does so. This one will continue moving to the left, and it will slow down as it does so. Now, if that net force were continued to be applied to that object after it stopped, it would eventually flip this arrow inside the box. So this object that's moving to the right would slow down, slow down, slow down, and eventually stop. And then if that net force continued, then it would start moving to the left. In that case, the net force in the direction would be the same, so it would speed up as it moved off the other direction. This is like throwing a ball up into the air. When you throw a ball up into the air, it's moving upward, but gravity pulls on it in a downward direction. So as the ball goes up, it would slow down, slow down, slow down, and eventually stop. If that downward force were to continue like gravity does, that object would then turn around and head the other direction. It would flip that arrow, in which case it would be pointing in the same direction as the object's motion, and the net force, it would speed up on its way to the ground. So two scenarios so far. If the net force is in the same direction as the object's motion, it will speed up. If the net force is in the opposite direction as the object's motion, it will slow down. There is a third and final option. Again, acceleration is speed and direction. It's change in either one of those or both of those at the same time. So when a net force is applied to an object in the same direction as its motion, it will speed up. Opposite direction of its motion, it will slow down. In any other direction, it will cause the object to change direction. It will turn. Now, I drew these all perpendicular because if that net force is perpendicular, that's all that will happen. The only thing that will occur is the object will turn. If it's at an angle, then it's going to either speed up and turn or slow down and turn at the same time. Perpendicular, the only thing that would happen would be the object would turn. So if we look at this object here, it is moving to the right, but there is a net force that's being applied upward. This object would turn upward. This object is moving upward while there's a net force to the right, so this object would turn to the right. This one's moving left while there's a net force downward. This one is going to turn downward. It will move at a constant speed in all three scenarios because this force is exactly perpendicular. There is no forward or backward component to that force. If that force had come in at an angle, say something like this object would still turn downward because there's still a downward component to that motion, but there is also a forward component to that motion in which it would speed up. You'd have to think a lot about the way you did component vectors to be able to figure out what it's going to do. There's a component of its motion that goes in this direction, and there's a component of its motion that goes in that direction. So part of this is going to make it speed up. The other part is going to make it turn downward. That's what we have here. We have our net force at an angle, and we know that this net force is going to have an x and a y component. There will be a portion that comes off in this direction, indicated with the blue arrow in x. There'll be a portion that goes in this direction, indicated by the orange arrow in y. Again, that vertical vector, the one that's perpendicular to the object's motion, is going to cause it to turn upward. And that blue vector, the x component, is in the same direction as the object's motion, so it would speed up. So the more than one thing could be happening at the same time when you have those angled vectors. As long as the vector is perpendicular, the only thing that the object will do is turn. If that vector is at an angle, then it's going to both turn and speed up or slow down. And predicting what's going to happen to an object is a big part of Newton's second law. Looking at what an object's doing while these net forces are acting on it, being able to apply that and make some kind of prediction about how the object's going to move in the future is an important conceptual part of this, not necessarily a mathematical part of it, but a conceptual part of this. Another angled vector, and again, we're looking at the x and y component. It's angled down and to the right, so there's going to be a right component, there's going to be a down component. That down component is perpendicular to the object's motion, so as it moves to the left here, it's going to turn downward because of that orange vector, that y component. And this x vector is opposite of its motion. This horizontal one is opposite of its motion. So that object is also going to slow down. Being able to make those predictions are a pretty important thing. Now there's two components, there's two variables that will affect how much it accelerates, the magnitude of that acceleration. And that is the mass and the force that is being applied to the object. The mass and the force that's applied will directly affect the magnitude or the strength of the acceleration that you see. Mass and acceleration are inversely proportional. Inversely proportional means they change in the opposite way. So doubling the mass of the object would cut the acceleration in half. Tripling the mass of the object would cut the acceleration to 1/3. 4 times the mass would be 1/4 of the acceleration, and vice versa. If I cut the mass in half, I'd have twice the acceleration, the inverse of one another. We can see this in everyday life with objects like toy car versus real cars. If you try to push a toy car, it accelerates very easily and accelerates very quickly. This is because the toy car has a small mass. If you apply that same force to a real car with a much greater mass, you're going to get much less acceleration out of it because of the much higher mass that that real car has. Force and acceleration are directly proportional. That means the more force you have, the greater the acceleration is going to be. They'll change in the same way. So doubling the force will double the acceleration. Tripling the force would triple the acceleration. Cutting the force in half would cut the acceleration in half. They change in the same way. A car will accelerate it faster if there are 3 people pushing on it as opposed to the 2 people that are in this picture here, because 3 people can produce a greater force than just 2 can. That greater force will give you greater acceleration. So mass and acceleration are inversely proportional. Force and acceleration are directly proportional. Again, another important conceptual side that you have to remember. Those relationships are expressed in the equation F equals m times a, or the force applied is equal to the mass of the object times its acceleration. Force equals mass times acceleration, F equals ma. Force is measured in a unit called newtons, named after Isaac Newton. it is what we call a derived unit, a kilogram meter per second squared. That's what force really is. But to simplify that and make it something that's easier to work with on paper, it has been simplified into something called a Newton. Mass is in kilograms and acceleration is meters per second squared. Those are the standard units for mass and acceleration. It's important to note that if you want to get newtons as an answer, mass does have to be in kilograms and acceleration does have to be in meters per second squared. If you had any other unit, you would have to convert them first if you wanted to get a force that was in newtons. And again, this kilogram meters per second squared is what a newton really is. It's just a combination of these two things. If we take mass times meters per second squared, this is what we're going to get. Kilogram meter per second squared. You're going to see this as we work through math problems to try to understand what the units are all about. I do want to point this out. The directly proportional and inversely proportional relationships that I just talked about with force and mass are all in this particular equation. If I wanted to rearrange this equation to solve for acceleration, it would be A equals F over m. I want to rearrange this equation so that I'm solving for acceleration instead of force. I divide both sides by m, and I'd end up with A equals F over m. If a variable ends up in the numerator of an equation, that means it is directly proportional. And force ends up in the numerator of this equation, indicating that there's a directly proportional relationship. And if you look at the equation, you can understand this. If my force is doubled while my mass stays the same, so let's say I started off with 2 divided by 1, my acceleration would be 2. If I doubled the force but kept the mass the same, I did a force of 4 over a mass of 1, my acceleration would also double. It would also be 4. That's a directly proportional relationship, and you get that directly proportional relationship whenever a variable is in the numerator of your equation. If a variable is in the denominator of an equation, it is an inversely proportional relationship. And here we see mass in the denominator of this equation, indicating that the acceleration and the mass are inversely proportional. If I doubled the mass while leaving the force the same, that would cut my acceleration in half. Again, let's just imagine we have a force of 1 and a mass of 2. My acceleration is 0.5. If I have a force of 1 and a mass of 4, doubled my mass, my acceleration becomes 0.25. Doubling my mass would make my acceleration half of what it was. So that inversely proportional relationship is seen in that variable being in the denominator. The relationships go across the equal sign. So again, it's what's over here and how it relates to what's over here. Force and acceleration are directly proportional. Mass and acceleration are directly proportional, or inversely proportional. So let's do a couple math problems. Work through some of the little twists and tricks that you might see along the way using the problem-solving approach that I've been using all along. First step is identify what these numbers are. 2,000 kilograms. Kilograms measure mass. Doesn't say a mass of, that's just based on our knowledge of what kilograms measure. It's acted on by 1,500 Newton force. Now, oftentimes, when it is a force, it's going to say force, because there's more than one thing that can be measured in newtons. Weight can be measured in newtons. So if it says force of, that means the newtons measure force. Typically, if the newton is just sitting next to the name of something, like a 1,500 Newton car, then it would be weight. Typically, force is going to say force somewhere in the question, so we know that that's what we're talking about. So the mass is 2,000 kilograms, the force is 1,500 newtons, and we want to know what the acceleration is going to be. We're trying to find A. Only one equation that has those three variables in it. F equals m over a. We will add more force-based equations as we go. So for now, though, this is it. This is all we really have to choose from. A substitute. I've got 1,500 newtons. That's my force. I've got 2,000 kilograms. That was my mass, and I'm solving for A. I'll divide both sides by 2,000 to solve for A. 1,500 divided by 2,000 is 0.75, and the unit is meters per second squared. Now, the way that that unit is calculated is based on what a newton is. Again, 1 newton is equal to 1 kilogram meter per second squared. If I were to replace this with kilograms meters per second squared, this is what I'm doing. It's 1,500 kilograms meters per second squared divided by 2,000 kilograms. And when I divide these out, these kilograms cancel out. And all I'm left with is meters per second squared. That's where my unit comes from for my answer. As long as you have newtons and kilograms, you know it's going to be meters per second squared. You don't have to worry about breaking it newton down into what it really is to figure it out. But as long as you have those memorized, that'll work. If you don't have those memorized, you need to derive it, then you have to know that 1 newton equals a kilogram meters per second squared. So again, a couple different ways of doing it. A lot of times when students get to these force equation problems, they stop writing the units into the equations because they know what the units are going to be. As long as I went in with newtons and kilograms, I know this is meters per second squared. If I went in with meters per second squared and newtons, I know my mass would be kilograms. There's kind of an assumption there that's made because of that newtons unit. But again, it only works if you go in with the right units. Let's take a look at this one. A 3,000 kilogram car is acted on by 1,500 Newton force. What's the acceleration going to be? 3,000 kilograms, that's the mass. 1,500 newtons, that's the force. We want to know what the acceleration is. We're looking for A. Same equation, F equals m over A. The force is 1,500 newtons. The mass is 3,000 kilograms. Be 1,500 divided by 3,000, 0.5 meters per second squared. Now I did these two problems side by side because I want to demonstrate what changing the mass does. In the first one, the mass was 2,000 kilograms. We increased that to 3,000 kilograms. We increased that mass of the car. And by increasing the mass, we decreased the acceleration. We went from 0.75 meters per second squared to 0.5 meters per second squared. Again, demonstrating that inversely proportional relationship. As we increased the mass of the car, we decreased the acceleration. Now, same 3,000 kilogram car that we had in the previous question, 3,000 kilograms here, continuing with 3,000 kilograms, but instead of applying a 1,500 Newton force, we'll apply a 2,500 Newton force and see what happens. Again, 3,000 kilograms is the mass, 2,500 newtons is the force. Again, we're looking for A. Again, that's my equation. The 2,500 newtons goes in the place of F. The 3,000 kilograms goes in the place of M. To solve for A, we have to move this 3,000 kilograms. We have to divide both sides by 3,000. So it's 2,500 divided by 3,000, which is 0.83 meters per second squared. And again, we did this so we can look at the effects of increasing force. When you have a 3,000 kilogram car and a 1,500 Newton force, the acceleration is 0.5 meters per second squared. When I took that force up from 1,500 newtons to 2,500 newtons, that increase in force causes an increase in acceleration. If you're ever taking a test and you're trying to answer a question about the relationship between the variables, and you don't remember what the relationship was between the variables, then just do a little math. You don't have to memorize equations, you get equation sheets. Even in AP classes, there's an equation sheet. Look at the equation for it, start throwing numbers into it, and see what happens. And you can figure out how the relationships work by just playing with the math. Let's take a look at this. I wanted to throw some signs into this. The signs are important, just as they are in a lot of other places, because they show us the direction of things. They're vector quantities. Again, positive typically means right or up, and negative means left or down. We want to know what force is required to slow a 1,750 kilogram car at a rate of negative 7.5 meters per second squared. The mass is 1,750 kilograms. Kilograms measure mass. And it doesn't say anything about this being an acceleration. It does say slow it at a rate, but it's that meters per second squared that's the giveaway that that's an acceleration. And negative just means it's to the left or opposite of the direction that that car is actually moving. We're looking for the force. Again, only one equation to work with that involves force for right now, F equals m times A. 1,750 kilograms, that's the mass. Negative 7.5 meters per second squared, that's the acceleration. We multiply those two together. You get negative 13,125 kilograms meters per second squared. Kilograms times meters per second squared. That is a Newton. The negative sign, again, is a direction. And it's important because force is a vector quantity, just like acceleration is a vector quantity. And that negative sign meant that the acceleration was in the opposite direction as the object's motion. We're assuming here that the object was moving to the right. This acceleration was to the left. That's what would slow it down. Again, Newton's second law. If the net force is in the opposite direction of the object's motion, it's going to slow down. We should expect a negative net force for our answer. So watch those signs. They are important. Let's take a look at this one. This is an example of a scenario we're going to have to use an old equation in order to get what you need to do the new equation. Things that happen all the time in a physics classroom. A car accelerates from 8 meters per second to 15 meters per second. These are both velocities, meters per second. The from tells me that that is the initial velocity. The to tells me that's the final velocity. In 3.5 seconds, seconds measure time. Car has a mass of 1,200 kilograms. That is the mass. What force is used to accelerate it? Now we know the equation to calculate that force is F equals m times A. To get the force, we need both the mass and the acceleration of the object. While we have the mass, we don't have the acceleration. So we're going to have to figure out what the acceleration is using the old equation, A equals delta V over T. First thing we have to do is figure out what delta V is. Delta anything is final minus initial. So delta V is VF minus VI. VF is 15 meters per second. VI is 8 meters per second. So when we subtract those out, we get a delta V of 7 meters per second. Then we can substitute. 7 meters per second goes in the place of delta V. Our time of 3.5 seconds goes where T is. 7 divided by 3.5 is 2. Meters per second divided by seconds would be meters per second squared. So then going back to our very first unit and one of the very first equations that we learned to find what the acceleration is, that missing piece in the force equation. And again, this is very typical of physics classes. It's one of the reasons why colleges love to see physics on a transcript. It's a real problem-solving course. I have to know that the equation for finding force is F equals m times A. Then I have to recognize that acceleration is missing. And then I have to recognize that I can use these pieces of information to find that acceleration, know what equations to use and how to do it. And then once I have that acceleration, then I can go ahead and substitute into F equals m times A 1,200 kilograms times 2 meters per second, then solve it out and get 2,400 newtons. So again, that typical higher level problem solving that you often find in a physics classroom. Let's take a look at this one, see what the twists are in this. An object with an initial velocity of 5 meters per second accelerates for 3.4 seconds while covering a distance of 40 meters. If the mass of the object is 50 kilograms, what force is used to accelerate it? So again, going through and just figuring out what I know. Initial velocity, VI, 5 meters per second. Accelerates for 3.4 seconds, that's a time. Distance, 40 meters, that's a delta x. Mass of the object is 50 kilograms. Those are all my givens. What force was used to accelerate? I'm looking for F. Again, right now I only have one equation that I can really use to solve for a force, and that is F equals m times a. And I recognize, well, I do know the mass of my object. I don't know my acceleration. So I'm going to have to find a way to use these three pieces of information to give me A. I can't use the acceleration equation this time because I don't have a VF. I have a displacement instead, which tells me I'm going to have to use a kinematic equation. So I go find the kinematic equation that has A, VI, T, and delta X in it. That would be the delta X equals VIT plus 1/2 AT squared equation. Substitute and solve for A. So my delta X is 40, my VI is 5 meters per second, my T is 3.4. 1/2, just a number that carries over with the equation. Again, it's part of that area of a triangle when we're working with a velocity time graph. That's where the 1/2 comes from. And then the time squared, 3.4 squared. Simplify first. 5 times 3.4 is 17. The seconds will cancel. All we'll be left with is meters. 1/2 times 3.4 squared is 5.78. The seconds do end up squared times A. So simplified, now I can solve. I'll subtract 17 from both sides first. That gives me 23 meters equals 5.78 seconds squared times A. And then I'll divide both sides by the 5.78 seconds squared. 23 divided by 5.78 is 4 meters divided by seconds squared. Again, finding a way to get the missing information you need. That's what physics is all about. I recognize when I look at that forced equation that I have a mass, but I don't have acceleration. And then I recognize that there is a way that I can use those three pieces of information provided to me to get that acceleration that I'm missing. This time going into kinematics. Now I can substitute and solve. The mass was 50. The acceleration is 4 meters per second squared. Multiply those together for an answer of 200 newtons. So a lot of thought goes into this. It's, again, good thought. This is a very good critical thinking class. This is what critical thinking is all about. Being able to look at a problem and trying to figure out how you're going to solve it. The trick in this one is dealing with the givens. A 2 Newton force, that's obviously force, is applied to a 550 gram toy car. Grams measure mass. What will the acceleration be? My issue is grams. Again, we got to always be on the lookout for units that have to be converted. In order to get my math to work with newtons, my math has to be in kilograms because a newton is a kilogram meter per second squared. If I go into my math with grams, I won't get proper unit cancellation and I won't get the right answer. Because a newton is a kilogram meter per second squared, my mass also has to have kilograms on it. So I'm going to have to convert. This is a basic metric conversion. King Henry died by drinking chocolate milk is the easy way to do it and the only way you have to do it. There's no reason to set up dimensional analysis. It takes longer. You would have to remember that there are 1,000 grams in a kilogram in order to do dimensional analysis. If you can remember, King Henry died by drinking chocolate milk. Kilo, hectodeca, base, deci, centi, milli. You can convert just by moving the decimal point. I have grams, which are a base unit. I'm going to go to kilograms, which is the K. That is 1, 2, 3 places to the left. Take the decimal point and move it 3 places to the left. And you've made your conversion, 0.550 kilograms. And that is the number that you're going to want to use when you do the math, not the 550. That way the units will cancel out the way they're supposed to cancel out, and you'll end up with meters per second squared as your answer. F equals m times a, that's the equation we're using. Force is 2 newtons, the mass we're going to go with 0.550 kilograms times a. To move the 0.550 kilograms, we have to divide both sides by it. 2 divided by 0.550 is 3.6. And the units will end up being meters per second squared. Again, this is a kilogram meter per second squared, and we are dividing it by kilograms. That will cancel the kilograms out and leave you with nothing but meters per second squared. If you went into this with the 550 grams, the units would cancel. You would have kilograms divided by grams, and there wouldn't be unit cancellation there. That's why we have to make sure that everything matches up like it's supposed to. The equation for Newton's second law can also be used to calculate the weight of an object. Weight is the measure of the pull of gravity on an object. It's a force. Then it's measured in newtons, just like every other force is. And because it is a force, because it is measured in newtons, we use the same equation to calculate it. It's just that the acceleration is going to be a given. It's going to be acceleration due to gravity. And that is going to be technically negative 9.81 meters per second squared. But in this case, we can ignore the negative sign. We can ignore the downward direction if we want to. Again, when we did kinematics, when we did free-falling objects, the acceleration due to gravity was negative 9.81 meters per second squared. We could use that here, but we would have to recognize that all of our weights are going to be negative. Because as forces, they're vector quantities, and they're going to have directions on them, and they're going to be pointing downward all the time because gravity points downward all the time. And we're going to have negative numbers. But really, nobody talks about their weight as a negative number. So if you want to go into this with positive 9.81 meters per second squared and not worry about the direction, that is perfectly acceptable in this case. W is weight, takes the place of force. Again, it's measured in newtons, just like any other force is. M is mass. Because we're dealing with newtons, again, it has to be kilograms. And AG is acceleration due to gravity, and it is 9.81 meters per second squared. So a couple real quick calculations. What's the weight in newtons of a 5 kilogram object? Well, 5 kilograms is my mass, and that appears to be the only thing I'm given in the question. But we do have a hidden number here. We have an assumed number here. Because we're talking about weight, the assumed number is that acceleration due to gravity, negative 9.81 meters per second squared. We're looking for weight. Yes, I'm using the negative sign this time. Mass times acceleration due to gravity, 5 times negative 9.81 meters per second squared, negative 49.05 newtons. And again, that negative sign just means downward. Somebody asks you your weight, you say, I weigh 130 pounds. You don't say, I weigh negative 130 pounds, because it's just assumed it's a downward force. So again, you can leave the negative sign on there and let the negative sign carry all the way through and get your answer that way. That would be a perfectly acceptable thing to do. You don't have to, though. You can use a positive number here. And if you use positive 9.81, you just end up with a positive weight. Now, if we did change our location, and instead of being on Earth, move somewhere like Mercury, that acceleration number would change. Earth is 9.81 meters per second squared. Mercury is 3.59 meters per second squared. It's a smaller planet with a lot less mass, so it has less gravity. That same 5-kilogram object would have a different weight on Mercury. Mass is 5 kilograms. Acceleration this time is 3.59. This time I'm not going to put the negative sign on it. We're looking for weight. Same equation. Substitute 5 kilograms times 3.5 times meters per second squared gives you 17.95 newtons. Again, you could have made that 3.59 negative if you wanted to, and the negative would have carried through all the way to the weight, again, just indicating downward, or leave it off. It's up to you. This points out why in science we use mass more than we use weight. Newton's first law is the law of inertia. The inertia of an object depends on its mass. The greater the mass, the greater the inertia. The lower the mass, the less inertia. In this unit, second law, we're talking about mass affecting acceleration. The greater the mass, the lower the acceleration. The lower the mass, the greater the acceleration. Mass, 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 mass. Everything's about mass. Why is that? Because it doesn't matter if you're on Earth or you're on Mercury, the mass is going to be the same. So the inertia of this object would be the same on Earth as it is on Mercury. The acceleration of this object would be the same on Earth as it is on Mercury. The mass is the one thing that doesn't change. The weight does. The weight will change from one place to another. That's why weight is not referred to very often in physics and not used as a variable in calculations too often because it changes. 1 pound is equal to 4.4 newtons. Again, we talked about this in the force video. 1 pound is equal to 4.4 newtons. It's approximately a quarter pound for every newton. What would the mass of a 145-pound person be? Look at what we got here. 145-pound person, that's a weight. And we're assuming on Earth, so the acceleration due to gravity is 9.81 meters per second squared. We want to figure out what the mass of that person would be. This is here, 1 pound is equal to 4.4 newtons, because pounds won't work in our force equation, or our weight equation, because our weights need to be in newtons. This is in newtons, this is in kilograms, that's in meters per second squared. So while we have meters per second squared for A, we do not have newtons for our weight. That means we're going to have to use that as an equivalence to do a dimensional analysis conversion before we can plug anything into this equation. Dimensional analysis always starts with the number you're given, the 145 pounds, times and then a fraction bar. The unit that we have here is the unit that we have to put on the bottom. So the 1 pound goes on the bottom, the 4.4 newtons goes on the top. And again, that's all because of unit cancellation. We need those pounds to cancel out. Can basically ignore the 1, the 4.4 is on the top, so we multiply by it. 145 times 4.4 is 638 newtons. Watch for those units. Make sure you have the units that you need to make the cancellation work the way it's supposed to in your calculation. Now we can substitute and solve. 638 newtons goes over here where W is. The 9.81 meters per second squared goes over here where AG is, and that really should be A sub G. And that. Divide both sides by 9.81 to solve. The mass of my object is 65 kilograms. Again, a newton is a kilogram meter per second squared. We need newtons so the meters per second squared from both of these can cancel out and leave us with nothing but kilograms. If we had gone into this with pounds, there'd be no unit cancellation, and so this wouldn't work. Make sure your units are the way they're supposed to be so that your answers and your units come out the way they're supposed to be. This is one that I alluded to earlier where newtons can be used to represent two different things. I have two things in this question that are measured in newtons. A 125 newton force is applied to a 200 newton object. This outright says force, and I said that's what it has to do. But typically when newtons are involved and it's a force, it's got to tell you it's a force. Because this other way, where it just says 200 Newton object, there's no word force here, it just refers to the object. That's a weight. So one of those newtons are a force, the other newton is a weight, and you have to be able to differentiate between which one it is. We're looking for how fast it's going to accelerate. Problem we have here is that the equation with acceleration in it is F equals m times a. While I have the force that's going to be applied to it, I don't have the mass. So I'm going to have to use the weight equation to figure out what the mass is. So again, using one equation to figure out missing information for the other, a very physics kind of thing to do. The 200 newtons is the weight, so you got to make sure you use the right one here. And again, it's just the one that refers to the object. It doesn't say anything about force. It says 200 Newton object. It's like saying a 5-pound bird. That'd be a pretty heavy bird, but a 5-pound bird. If the force is attached to the name of the object, that's just the weight of that object. Divide both sides by 9.81 to solve. 200 divided by 9.81 is 20.4. This is kilograms meters per second squared. It's being divided by meters per second squared. So all you're left with is kilograms. That's how you get your mass. And then once you have your mass, you can substitute the 125 newtons. That's the force. Again, make sure you're using the right one. The 20.4 comes over here. And again, you'll know this is the right one because it says force on it. 125 divided by 20.4 is 6.1. This is kilograms meters per second squared. That is kilograms. When we divide this by kilograms, all we're left with is meters per second squared. A lot of math, I know. It's a couple of simple equations made more complicated by unit conversions and having to do multiple steps, multiple equations in order to get to your answer.